Hello everyone, and welcome to this POPL talk on the fine-grained and parallel complexity of Andersen's pointer analysis. I am Andreas Pavlogiannis from Aarhus University, and this is joint work with Anders, Alnor, Mathiasen. It is well accepted that pointers make static analysis hard because extra effort has to go into the aliasing effects that they might have in the analysis. For example, in this program, the value of C depends on whether A and B are aliases, meaning whether they point to the same memory location. Because of such effects, pointer analysis is very often a first step in the analysis pipeline, which means that it has to be fast but also precise, as the quality of the overall analysis depends on the precision of the pointer information. Now, as usual in static analysis, pointer information can be modeled at various degrees of precision. Perhaps the most popular analysis is Andersen pointer analysis, which Andersen published in his thesis in '94. As you can see, the thesis is very heavily cited and serves as the basis of many papers coming out to this day. It is a flow-insensitive analysis that does not capture nested pointer dereferences, and it is based on a so-called inclusion principle. So let me give you the big picture behind this principle. At any point, the analysis offers a static view of may points to information. For example, here we have that during the execution of the program, pointer A may point to variables B and E, while pointer D may point to C. The analysis proceeds by examining what pointer altering statements the program contains. For example, the statement C takes the address of A, tells us that C may point to variable A during the execution, which is modeled by drawing this extra edge from pointer C to the memory address of A. An assignment statement E equals D tells us that E may point to whatever addresses D may point to, and thus we have this new blue edge. A statement B equals star E tells us that B may point to any addresses pointed by pointers that E may point to. Here we already know that E may point to C and C may point to A, therefore B may also point to A. Finally, a statement star D equals A tells us that all the pointers pointed by D may be assigned to A, and thus may point to whatever E points to. Since we have already discovered that D may point to C, we conclude that C may point to B and E. I hope this gives you the general idea. Formally, the analysis is stated as the least fixed point of a set of inclusion constraints between the points to set of all pointers, where the constraints generalize the principle we illustrated in the previous slide. For example, the statement A equals B results to the constraint that the points to set of B must be included in the points to set of A. This yields the computational problem of the analysis, where the input is a set A of n pointers and a set S of m statements that manipulate these pointers, and the statements can be as many as quadratic on the pointers. The analysis has two popular goals in the literature. In the exhaustive case, we have to return the points to set of each pointer A, whereas in the on-demand case, we only need to determine whether a specific pointer A may point to a specific address B. So the exhaustive case has output size n squared, since each of the n points to sets may contain n pointers, whereas the output in the on-demand case is just a single bit. Despite the big impact of Andersen's pointer analysis, its computational complexity has been poorly understood. So in one sentence, this paper draws a rich landscape of the complexity of the analysis in various natural settings. The talk consists of two parts. The first part is a tour over the results of the paper, with a brief stops along the way to make some intuition, and the second part is a bit more technical and deals with the problem of Dike-1 reachability. In part A, we make a connection of this problem to Andersen's analysis, and in the second part we present details of the new algorithm for solving D1 reachability, which gives the best bound of the problem so far. So first we examine the general complexity of the problem. It is well stated in the literature that the analysis can run in cubic time. However, a closer look reveals that the term cubic is not very specific and has not been used very consistently. Recall that we have two parameters, n, which is the number of pointers, and m, which is the number of statements, and m can be as large as n squared. So the term cubic in the literature has had many forms, ranging from m cubed to n squared m to even n to the fourth. Note that each of these is above the n cube bound in the general case, so as a first step in understanding the complexity of the problem, we saw that Andersen's pointer analysis can be computed in time that is cubic in the number of pointers, regardless of the number of statements. The next question is whether this n cube bound can be improved further, for example, maybe become n squared. Here we make a crucial distinction between the two variants of the problem, meaning the exhaustive analysis and the on-demand analysis. It can be easily shown that the exhaustive case can encode the transitive closure of a graph, which directly implies a combinatorial cubic lower bound for the problem. However, in this reduction, on-demand pointer analysis corresponds to a single-pair reachability problem, and since the latter is solvable in quadratic time, there is hope that on-demand analysis also admits a subcubic bound. We resolve this question by showing that even the on-demand analysis has a conditional cubic lower bound under standard complexity theoretic hypothesis. This tells us that in the general case, on-demand analysis is no easier than exhaustive analysis, while the hardness of the analysis does not come from the requirement to produce large outputs, as the cubic lower bound also holds when the output is just a single bit. As for the proof, we obtain it by showing that doing on-demand Andersen analysis is at least as hard as detecting whether an undirected graph contains a triangle, meaning a clique of size 3, which in turn has a combinatorial cubic lower bound. Now, a popular approach to speeding up static analysis is by looking for approximate solutions. This is achieved by restricting the search space by bounding the size of the witnesses. Since we have seen that even on-demand Andersen's analysis is unlikely to admit a subcubic bound, we proceed to investigate whether such improvement exists under witness bounding. To make this witness bounding a bit more precise, recall that the result of the analysis is defined as the least fixed point of points to sets of pointers reached by executing these 4 types of pointer statements. It can be shown that on our way to the fixed point, each of these statements might be executed quadratically many times in the worst case. So we can perform witness bounding by bounding the number of times a particular statement or a type of statement is executed when looking for witnesses to the points to information. For example, what happens if we are only allowed to execute logarithmically many statements of the form star d equals a instead of quadratically many? Can we solve the problem any faster in this case? A bit more formally, we obtain the ij bounded version of the problem for integers I and j by looking at the points to sets as witnessed by executing sequences of statements that only have j application of statements of type I. Perhaps surprisingly, we saw that if we require the number of statements of type star a equals b to be bounded by a polylogarithm, then the problem can be solved in nearly matrix multiplication time, meaning much below the cubic bound. On our way to this bound, we solve another important problem in static analysis, that of Dijk-1 reachability. So let me give you some flavor of how the two combine. A closer look at Andersen's analysis reveals that if we assume that there are no statements of type 4, and thus we only have these 3 types of statements, the problem becomes isomorphic to the well-known Dijk reachability with only one parenthesis type, which is also known as reachability in one-counter systems. The idea is that these 3 statements on the left imply an assignment d equals a on the pointer analysis world, whereas on the Dijk reachability world, if we interpret taking the address of a variable as opening a parenthesis and dereferencing on the right-hand side as closing the parenthesis, we have a reachability relation a reaches d. So, to solve the bounded analysis where we limit the number of applications of type 4 statements to be j, we may simply solve j instances of the Dijk reachability problem that is implied by the other 3 types of statements. In each iteration, after we solve the Dijk reachability problem, we apply all the type 4 statements that are applicable due to the new reachability information discovered, and we repeat. So the complexity of this process is j times the complexity of solving Dijk-1 reachability in each iteration. In the paper, we show that Dijk-1 reachability can be solved in time n to the omega log square n, which also establishes the best complexity bound for the problem. Now, let's take a closer look at the new complexity of the analysis under witness bounding. This is essentially n to the omega. In turn, omega is a constant currently around 2.3 and keeps decreasing, while it is believed that the true value of omega is asymptotically 2. So in that limit, our bound of the theorem above becomes almost quadratic. A very natural question is again whether witness bounding admits a bound below quadratic, for example of the form n to the 2 minus epsilon for some positive epsilon. It turns out that no, and our upper bound is also tight. In the paper, we prove that even if we bound all types of statements to be logarithmic, not just the type 4 statements, the problem is orthogonal vectors hard and thus unlikely to admit a subquadratic bound. For context, the problem of orthogonal vectors is a simple problem where we are given two sets of d-dimensional binary vectors, and the task is to find a pair of vectors in the two sets that is orthogonal. The problem has a simple quadratic solution, and it is believed that no truly subquadratic bound holds when the dimension is high enough. Now, in the paper, we saw that a subquadratic solution to the on-demand Andersen's analysis with logarithmically bounded witnesses would imply a subquadratic solution to the orthogonal vectors, and thus Andersen's analysis is at least as hard as orthogonal vectors. Our results so far characterize the fine-grained complexity of Andersen's analysis. Finally, we turn our attention to the parallel complexity of the analysis. There are various papers that propose parallel solutions for the analysis, which leads to speedups over sequential algorithms in practice. Hence, the natural question here is whether the analysis is truly parallelizable, meaning whether such speedups are accidental or are guaranteed to exist in all instances of the problem. Our first result shows that Andersen's pointer analysis is polynomial time complete and thus not parallelizable. Our reduction is from the monotone circuit value problem, or monotone CVP, which takes as input a monotone Boolean circuit and evaluation of the inputs and asks to determine the value of the output. This is one of the standard polynomial time complete problems and thus unlikely to be parallelizable. In the paper, we saw that Andersen's analysis can model monotone CVP under log space reductions and thus is also p-time complete. On the other hand, we show that if we again focus on the bounded version of the analysis, then it becomes perfectly parallelizable. In particular, recall that given some integer I, the class NCI is the class of problems that can be solved in time log to the in while using polynomially many processors. For example, matrix multiplication is in NC1, whereas graph reachability is in NC2, while the union of all these NCI classes gives the class NC of problems that are considered to be perfectly parallelizable. In the paper, we show that bounding the number of type 4 statements to be log to the I brings the problem in NCI plus 2, and thus if we only look for witnesses where type 4 statements are polylogarithmically bounded, then we get really fast parallel algorithms for the analysis. This concludes the first part of this talk. In summary, Andersen's analysis is one of the most popular static pointer analyses, but despite its widespread use, its complexity has been poorly understood. This paper draws a rich landscape of the complexity, where we establish cubic upper and lower bounds, and we saw that a form of witness bounding brings the problem to matrix multiplication time, while we also establish the best bound for the Dike-1 reachability in the same time. In addition, we show that witness bounding has a quadratic lower bound, and thus the upper bound is almost optimal. Finally, we see that the analysis is not parallelizable in the general case, but witness bounding again makes it parallelizable. Thank you for your attention. Now, for those interested in more details, we now proceed to the second part of the talk, where we sketch our new algorithm for Dike-1 reachability and the complexity bound it yields. Recall that in Dike reachability, we are given as input a set of k different parenthesis types and the Dike language over these parentheses, as well as a directed graph whose edges are labeled with these parentheses. The task is to compute reachability information as witnessed by paths whose labels along the edges produce a string that belongs to the language. For example, in this graph, we have that x reaches z because the red path produces a string of matching parentheses, but x does not reach w even though we have an edge from x to w. So the problem of Dike k reachability is, given a Dike graph G, compute all pairs Dike k reachability. So how fast can we solve it? When k equals 0, the problem becomes standard graph reachability, which is solvable in n to the omega time, as the transitive closure can be encoded in matrix multiplication. When k is at least 2, the problem is solvable in cubic time, and it is believed that no subcubic algorithm exists. In this paper, we obtained that type 1 reachability is solvable n to the omega log square n time, meaning only log square n times slower than the standard graph reachability. So what is the turning point from k equals 2 to k equals 1 that allows the subcubic breakthrough? When k equals 1, the underlying stack alphabet becomes unary and the stack behaves like a counter. This has very distinct qualitative implication because when k equals 2, the shortest path that connects any two nodes can be exponential in length. On the other hand, when k equals 1, all reachability witnesses become at most quadratic in length, so the algorithm that we propose here exploits this property of polynomial witnesses for k equals 1. So to explain the algorithm in pictures, for any path that connects two nodes, we consider the value of the counter along the way. In this picture, the counter initially increases, then stays the same, then decreases a bit, then it increases again, and so on. At first, we will simplify the problem and only focus on reachability that is witnessed by what we call bell-shaped paths. These are paths that have only one local maximum, meaning that if the counter decreases, it never increases again. To make the problem even simpler, let's consider what happens if we focus on bell-shaped paths where the counter never exceeds 1. This means that the counter can see at most one increment, as the bound of 1 disallows successive increments of the counter, while the bell shape of the path disallows the counter to increase after it has decreased. We can solve the problem easily by creating two copies of the graph, where the first copy corresponds to nodes when the counter is 0, and the second copy corresponds to nodes when the counter is 1. In our example here, when we go from A to B, we increase the counter, which is captured on the right by jumping from the first to the second layer of the graph. Similarly, when we go from D to E on the left, we decrease the counter, which is captured on the right by jumping from the second layer to the first. It is easy to see that computing standard reachability on the right will capture all bell-shaped paths that have the counter bounded by 1. Now, in general, it will also capture non-bell-shaped paths, but this is not a problem as all reachability witnesses on the right are valid. So our solution works when the counter is bounded by 1. Now, how do we proceed with larger counter values? The idea is a common trick in computer science known as successive doubling. And here is how it works. We create 3 layers of the graph, same as before. We compute all pairs reachability on a 3-layered graph, and besides the bell-shaped reachability with counter bounded by 1, as shown in this red path, the transitive closure on this graph will also reveal reachability between the first and the third layer, which captures paths where the counter is monotonically increasing and decreasing in the interval 0 to 2. In the next iteration, we insert the reachability summary edges we found in the previous step. For example, now we have the extra edge from C to E. Moreover, the edges between the layers 1 and 2 are the reachability relationships between layers 1 and 3 in the previous graph. So now computing the transitive closure on the new graph will reveal that node A reaches node E via the bell-shaped path where the counter is at most 3, and similarly from B to D. Repeating this one more time, the layers of the graph now correspond to jumps of the counter by 4 units and so on. In the end, we have computed all bell-shaped reachability. So how long does this computation take? In each iteration, we perform a standard transitive closure, which takes n to the omega time asymptotically. Now, how many iterations do we have to perform to capture all bell-shaped paths? Notice that every iteration doubles the counter value. Moreover, the maximum counter value cannot exceed the length of the path since we can only add 1 at each step. But since the maximum path length is only quadratic, the maximum counter value is at most quadratic, hence we only require 2 log n iterations for a total time of n to the omega log n. So this concludes that we can solve bell-shaped reachability in n to the omega log n time. So what about the general case? In general, reachability might not be witnessed by bell-shaped paths, but rather by paths that look like this that have multiple bells. However, after computing bell-shaped reachability, all the bells of this path have been summarized by simple edges shown here in dashed red. Notice that the new red path has fewer bells than the initial path. At this point, we may repeat bell-shape reachability one more time, and the new summary edges create a blue path that is itself bell-shape. So, if we compute bell-shape reachability one last time, we will capture this path and thus the initial black path. So the crucial question here is how many iterations do we need to perform? And here is the key observation, which is just beautiful. Suppose that after performing one step of bell-shape reachability, the initial black path has been summarized by the red path, and the red path has a local maximum in this counter value. Now, how can the black path continue? If it decreases the counter, then there is another red path that performs summarization at this lower level, so we can repeat the argument for this new path. On the other hand, if the black path increases the counter, then on its second way down, it will create a new bell. Now notice how these two successive bells are nicely summarized by a single bell of the red path. This is not accidental. We can show that in every iteration of bell-shape reachability, the number of bells of the summary path halves compared to the original path. And since the number of bells of the original path is bounded by the length of the path, we have at most quadratic bells originally. Hence, this halving of bells has to happen only logarithmically many times, meaning that we have to compute bell-shape reachability only logarithmically many times. And as we have seen earlier, each iteration takes n to the omega log n time, thus the total time for computing Dike 1 reachability is n to the omega log square n. This brings us to the end of this second part. Thank you for your attention and your interest in the details.